Let's begin tonight with a crime scene. A small, domestic one. Imagine the sound, just the pure sound, of a glass slipping from a hand and striking a hard floor. There is that sharp, crystalline crack, followed by the scattering, skittering music of 100 fragments dancing to a stop. The event is over. It is absolute. It is irreversible. The universe has committed itself to this new state of affairs, a puddle of liquid, a collection of broken pieces. You cannot unshatter the glass. You cannot unspill the water. Every instinct in your body, every memory you possess, confirms this fundamental truth. The story only runs one way. But here is a secret, a deep, unsettling secret that physicists whisper about in the quiet of their laboratories. The fundamental laws that governed every moment of that catastrophe. The law of gravity that pulled the glass down, the electromagnetic forces that held its atoms together and then failed, the laws of motion that sent the shards flying. Every single one of those laws is utterly indifferent to the direction of time. If you were to film that event and run the movie in reverse, the laws of physics would be perfectly happy with what they saw. The shards gathering, the liquid coalescing, the glass leaping back into a waiting hand. From a purely mathematical standpoint, that series of events is just as valid, just as physically permissible as the one we actually witnessed. The laws have no preference for which way the story runs. They contain no arrow. So, here is the real crime scene, the great intellectual mystery we must investigate together. How does a universe built on perfectly reversible rules produce the unwavering one-way street of our lives? How does the absolute certainty of what's done is done emerge from a set of instructions that doesn't care about the difference between before and after? This discrepancy, this chasm between the fundamental code of reality and our lived experience of it, is not a minor detail. It is perhaps the most profound paradox in all of science. And it hints that our common-sense notion of time, the gentle, flowing river we imagine ourselves drifting down, is a profound illusion. If that illusion begins to crack even in a simple kitchen accident, imagine what happens when we take it to places where the universe's rules are pushed to their absolute breaking point. Places where gravity becomes so intense that it tears the fabric of reality apart. These are not just theoretical curiosities. They are real objects scattered throughout our galaxy and beyond. These are the places where time itself comes unstitched from the rest of the cosmos. Imagine falling toward one. In your own private experience, inside your own vessel, your journey might take only a few minutes. Your watch ticks normally, your heart beats steadily. But in those few minutes, your personal timeline desynchronizes from the great clock of the universe. For an outside observer perceiving you from a safe distance, your final moments stretch out to encompass the entire future history of everything else. The fall of empires, the birth and death of stars, the slow cooling of the cosmos, all of it happens in the time it takes you to cross an invisible line. Your private forever becomes a mere blink of an eye for the universe you left behind. And the mathematics, the cold, hard equations written down by Albert Einstein, tell us something even more bizarre. They say your journey doesn't just end at infinity, it continues somehow to a place beyond infinity. What could that possibly mean? What happens when time runs out of numbers and just keeps going? And that is not even the wildest part of this cosmic tale. Your 11 minutes of personal experienced time, according to the intricate mathematics of the theory, correspond to a temporal destination that can only be described as being beyond infinity for that distant outside world. What does that even mean, beyond infinity? How can there be something after everything has already happened? It's a concept that our language, forged in a world of clocks and calendars, struggles to contain. If time can behave in such a bizarre and paradoxical manner out there, in the extreme, crushing conditions of deep space, then what in the world is time here for us? What is this phenomenon that we feel in every fibre of our being, in the steady beat of our hearts, in the rhythm of our breath, every single second of every single day, but that just crumbles into a collection of confounding paradoxes the moment you try to examine it too closely? And this question, this deep and profound inquiry, is not just some philosophical puzzle to be debated in quiet wood-panelled rooms. It is one of the most fundamental, most pressing problems in modern physics, a central mystery at the heart of our quest to understand the universe. And it's possible, just possible, that we might have just cracked a piece of it, pried open a tiny window into its true nature. You often hear people say, perhaps with a sigh of resignation, that there is no real progress in fundamental physics anymore, that the great heroic age of discovery is over, that all the big questions have been answered. That is the most profoundly mistaken idea one could hold. Just recently, within the quiet methodical world of mathematics, there was a colossal breakthrough on one of the greatest challenges ever laid down for the human mind, a problem that has stood unsolved for over 125 years. It's the famous sixth problem, one of a legendary list proposed by the great mathematician David Hilbert. And this breakthrough, this monumental intellectual achievement, doesn't just solve an old, dusty math riddle. It does something far more profound. It ties together three of the most important and seemingly disparate theories in all of physics. And finally, it shows with rigorous, unassailable logic how irreversible behavior, the one-way flow of time that we all experience, emerges from physical laws that, at their most fundamental level, are completely reversible, completely symmetrical in time. It's a huge step, a towering landmark in our intellectual landscape. And consider this: it was mathematicians who achieved it, not physicists. Physicists, I suppose, were busy with other important, but perhaps less fundamental tasks like redefining the kilogram with ever greater precision, or building ever more powerful particle colliders. This was a victory for pure thought, for the power of abstract reasoning to illuminate the concrete workings of the world. So, to truly grasp the scale of this achievement, to feel its historical weight, you have to allow your mind to drift back in time, back to the year 1900. The world was on the cusp of a new century, a time of immense optimism and technological change. In Paris, a brilliant German mathematician named David Hilbert, one of the last great universalists in his field, stood before the International Congress of Mathematicians and laid out a list of 23 unsolved problems. These were not mere curiosities or puzzles. They were intended to be the guiding lights, the great challenges that would shape the course of mathematical research for the entire 20th century. And they did. Some of these problems have since been solved, leading to entire new branches of mathematics. Some remain stubbornly, tantalizingly wide open, their solutions still beyond our grasp, and some are so vaguely worded, so philosophical in their scope, that we're still engaged in lively debate about what it would even mean to declare them solved. But one of the most ambitious, most far-reaching of all these challenges is number 6. In his sixth problem, Hilbert issued a grand demand, a call to action for the entire scientific community. He called for an axiomatic foundation for all of physics. In other words, he wanted physicists to stop what he saw as a somewhat haphazard process of just making up equations that happen to describe their experimental results, and instead to derive these equations logically and rigorously from a small set of clearly defined fundamental assumptions, from axioms. He wanted physics to have the same logical certainty as Euclidean geometry, where complex theorems are built step by step from simple, self-evident truths. If that could be done, if the entire edifice of physics could be placed on such a solid and logical foundation, it would solve one of the greatest mysteries of our existence. Namely, why does time only flow in one direction? Why does the river of time have a current that carries us ceaselessly from the past, through the present, and into the future? Because consider this fundamental paradox. On the atomic level, on the microscopic scale where the true laws of nature operate, moving forward in time is no different from moving backward in time. The laws of physics that govern this realm are time-symmetric. Sir Isaac Newton's laws describing the collisions of tiny particles, for instance, work exactly the same if you run the film of the collision in reverse. The particles would simply retrace their paths. There is no inherent preference for one direction of time over the other. But in our everyday lives, in the macroscopic world we inhabit, that is obviously, glaringly not the case. A shattered teacup does not spontaneously reassemble itself. gathering its fragments from the floor and leaping back onto the table. We remember the past, our minds filled with a rich tapestry of experiences, but we do not remember the future. We can only anticipate it, guess at it, hope for it. So how does this one-way world, this world of cause and effect, of aging and memory, emerge from the two-way, time-symmetric laws of the microscopic realm? Yes, you have undoubtedly been told the standard explanation. You've been told it's about entropy, about the relentless increase of disorder in the universe, and that is probably correct, in a broad sense. It is a powerful and intuitive idea, but the crucial point, the point that Hilbert was making all those years ago, is that it has never been rigorously mathematically proven for the laws of physics that actually describe the behavior of atoms and molecules. And that was Hilbert's central challenge. Stop making up plausible-sounding explanations and stories. Derive them. Prove it. Show the mathematical steps that take you from the reversible world of colliding particles to the irreversible world of our experience. Hilbert suggested that a good place to start with this monumental sixth problem would be to understand how the equations of fluid dynamics, the very equations that describe the flow of air around an airplane wing or the swirling currents of water in a river, arise from the motion of the individual atoms that make up that air and water. I mean, it seems obvious, doesn't it? Liquids and gases are made of countless tiny particles, right? So in principle we could just track every single molecule, apply Newton's laws to each one, and predict the behavior of the whole system. But in practice this is utterly impossible. There are way too many of them. A single glass of water contains more water molecules than there are stars in the known universe. So physicists use three different theories, three different levels of description, depending on the scale you're looking at. On the most fundamental microscopic level, the particles, the individual atoms or molecules, basically follow Newton's laws of motion. They fly through space and bounce off each other like an impossibly vast number of subatomic billiard balls. This is a reversible world, a world with no inherent distinction between past and future. If you knew the exact position and velocity of every particle at one moment, you could, in principle, calculate their entire past and future history with perfect precision. There is no arrow of time here. Then, on the intermediate or mesoscopic level, we take a step back. We give up on tracking each individual particle and instead concern ourselves with their statistical average behavior. We don't care about what one specific molecule is doing, but rather about the overall distribution of speeds and directions of all the molecules in a small region. This statistical description is governed by what is called the Boltzmann equation, named after the brilliant and tragic physicist Ludwig Boltzmann. And right here, at this statistical level, the arrow of time mysteriously appears, because statistics, by its very nature, introduces a direction. A system is far more likely to evolve from an ordered, improbable state to a disordered, probable one than the other way around. Irreversibility is born from probability. And finally, on the macroscopic level, the world of our direct experience, we zoom out even further. We no longer think about particles or statistics at all. We treat the fluid, the air or the water, as a continuous medium, a smooth substance with properties like pressure, density and velocity. This is the world described by the celebrated equations for the flow of fluids, the Euler and Navier-Stokes equations. This is the world we live in, the world of weather forecasts predicting the movement of vast air masses, and the world of aerodynamics designing the shape of wings to generate lift. Each of these three descriptions works beautifully within its own domain. We have Newton's laws for the micro world, Boltzmann's equation for the meso world, and Navier-Stokes for the macro world. And we have always expected, always believed, that the higher, more abstract levels can be derived from the lower, more fundamental ones. But Hilbert, with his relentless demand for rigor, asked, well, where is the derivation? Where is the mathematical proof that if you take trillions upon trillions of tiny hard spheres, obeying Newton's laws, and you mathematically zoom out from their chaotic dance, you first get the statistical behavior described by the Boltzmann equation, and then, as you zoom out even further, you get the smooth continuous flow described by the equations of fluid dynamics. And that is exactly what the authors of this new, not yet peer-reviewed, but incredibly important paper have apparently done. It's a long, technically dense paper filled with mathematical notation that is impenetrable to the layperson. But from the initial analysis by experts in the field, it appears that they have actually solved this central part of the problem. They have built the mathematical bridge that was missing for more than a century. They showed, with painstaking rigour, that if you take a huge number of tiny hard spheres bouncing around in a box according to Newton's laws, then as you properly scale up your perspective, you first derive the Boltzmann equation, and then from that, you derive the equations of fluid dynamics. This had been attempted before, many times, but the previous results were only approximate and, crucially, they only held for very, very short periods of time. The main difficulty, the great mountain that generations of mathematicians had failed to climb, was extending that short-term result to longer, more meaningful periods. To do this, these researchers developed a brilliant and novel way of tracking and classifying all the possible collision histories of the particles, and then evaluating their probabilities with unprecedented precision. In a way, it is a straightforward calculation, but the devil, as always, is in the overwhelming, mind-boggling complexity of the details. They had to tame an infinity of possibilities. So why is this such a big deal? Why should we care about a dense mathematical proof connecting different sets of equations? Well, for one, it rigorously justifies the equations we use every single day in countless fields of engineering, in weather prediction, in aerodynamics, and in climate modelling. We now know, with mathematical certainty, that these equations are not just good guesses or clever approximations that happen to work. They follow directly, logically, from the fundamental laws of motion governing individual atoms. It places some of our most important practical science on a foundation of solid granite. But, and this is perhaps even more interesting and profound, it shows in exquisite mathematical detail how irreversible behaviour, how the arrow of time, can emerge from perfectly reversible laws. It gives us the precise recipe for how the future becomes different from the past. It's like the first concrete step toward answering a question posed by the great science fiction writer Isaac Asimov in his famous short story, The Last Question. How can we, on a cosmic scale, decrease the net entropy of the universe? That, I think, is the ultimate question that any form of conscious living being in the universe will eventually be forced to ask as the cosmos ages and grows more disordered around it. But as impressive and groundbreaking as this breakthrough is, it is important to understand that it doesn't completely solve Hilbert's sixth problem, not by a long shot. I mean, that problem, in its full ambition, also demanded an axiomatic foundation for quantum mechanics, for Einstein's theories of relativity, for the perplexing phenomenon of turbulence, and for a whole bunch of other physical mysteries. So, the problem isn't totally solved, but one massive, crucial piece of the puzzle just clicked satisfyingly into place. We saw for the very first time, mathematically, how the one-way river of time is born from the timeless chaotic dance of reversible collisions. But what is this river? Does time really flow? On April 18th, 1906, at precisely 5:12 in the morning, a great earthquake shook the city of San Francisco. That event is fixed in history. The time of that event doesn't move. You can look it up in any history book or online encyclopedia. It is anchored in the past. What does move? What does flow? Is the meaning of the word now. Our consciousness seems to be progressing, changing, advancing through the landscape of time. The now of this moment will, in the next moment, become the past. Or perhaps it makes more sense to say that it is time that is flowing past our stationary now. This whole issue of movement is notoriously tricky to describe without falling into circular reasoning. When we say a car is moving, we are describing a change in its position over a certain interval of time. We note its position at one time and then its position at another, later time. The velocity is the distance it moved divided by the time it took to move that distance. This very simple and useful approach fails miserably when we try to apply it to the movement of now. Now is right now. Pause for a moment and consider this. Now is still right now. Is it moving? Yes, the movement of time is illustrated by the fact that the meaning and content of now keeps changing. At what rate does time move? The only answer we can give is a tautology, 1 second per second. It's a statement that tells us nothing at all. And then there's a third view to consider. The idea that new time is not just being traversed, but is being actively generated moment by moment, and this newly created time constitutes the now. The universe is growing not just in space, but in time. Are these views merely philosophical differences, different ways of speaking about the same phenomenon, or are they physically distinct? Is it a matter of personal choice which metaphor you prefer, or is there more truth in one than in the other? Suppose for a moment that time stopped. Would you notice? How could you? The very act of noticing requires time to pass. What if it moved forward in fits and spurts, lurching ahead and then pausing? Or what if it moved at a totally different rate than it does? Could you possibly detect the difference? Not easily, at least if you accept the depiction of time commonly used in movies and stories. Our human perception of the movement of now, the subjective flow of time, seems to be determined by the number of milliseconds it takes to send a signal from our sensory organs, our ears, our skin to the brain, and for the brain to process, record, notice, and remember it. For a human, that processing time is on the order of a few tenths of a second. For a housefly, it's a few thousandths of a second. That's why it is so incredibly difficult for a human to swat a fly. To the fly's rapid-fire consciousness, your threatening hand approaches in what seems to be agonizing slow motion, giving it ample time to escape. The rate of time isn't just a science fiction quandary or a biological curiosity. Einstein's theory of relativity gives us specific verifiable examples, most famously in the twin paradox. One twin traveling in a spaceship near the speed of light experiences less time than the twin who stays at home on Earth, and yet the travelling twin feels no difference in their subjective experience of time's flow. Their heart beats at a normal rate. Their thoughts proceed at a normal pace. The two twins experience the passage of time in the same manner, even though the objective flow of time for each of them is quite different from the perspective of the other. It was exactly this theory of relativity that was the first great step toward understanding the flexible, strange, and rubbery nature of time. To understand what now is, we first have to immerse ourselves in Einstein's world, a world where time slows down, where space contracts, and where the simple idea of two things happening at the same time, simultaneity, is just an illusion dependent on your point of view. To make this incredible breakthrough, Einstein had to perform a radical act of intellectual demolition. He had to go back to his childhood, to the very first principles. He threw out all the complex, sophisticated concepts of 19th century physics and started with the basics. With things that seem so obvious they are not even worth mentioning. In his revolutionary 1905 paper on special relativity, he didn't start with complex differential equations or abstract principles. He started at a train station. If, for instance, I say, he wrote in his characteristically simple and direct style, that the train arrives here at 7 o'clock, I mean something like this. The pointing of the small hand of my watch to 7 and the arrival of the train are simultaneous events. You might read that and think, what could possibly be simpler, more trivial? Who was he trying to explain this to? First graders? But in this deceptive, almost childlike simplicity lay the core of his genius. Einstein knew that to make a true breakthrough, you have to demolish the hidden prejudices, the unstated axioms that even his most brilliant colleagues believed in without even realizing they were beliefs. He had to expose these assumptions, drag them out into the light of conscious thought, and show that they were not obvious at all, and more importantly, that they were not true. He went back to the very first principles you were taught as a child when you first learned to tell time. Principles like the universality of time, the idea that even if individual clocks are sometimes off, they can in principle all be synchronized to a master clock, and that when your parent says do it now, the moment now for you and for them is precisely the same thing. Einstein came to the revolutionary conclusion that these seemingly unshakable truths were a lie. He realized he had to pull out one single, wrongly placed piece from the great jigsaw puzzle of the universe, a piece that was preventing the whole picture from coming together. And that crucial, misplaced piece was called simultaneity. Try for a moment to go back to your own childhood too. Remember how you felt time. Summer vacations filled with long sun-drenched days seemed to fly by in a flash, but a visit to the dentist's office or waiting for your mother to finish shopping at the shoe store seemed to drag on for an eternity. Einstein himself, as reported by the New York Times in 1929, was fond of a playful joke to explain this subjective nature of time. When you sit with a nice girl for 2 hours, you think it's only a minute, but when you sit on a hot stove for a minute, you think it's 2 hours. This childish, intuitive feeling of time's flexibility, of its ability to stretch and shrink depending on the circumstances, turned out to be profoundly prophetic. 10 years after his initial papers, Einstein published a new, even deeper and more comprehensive explanation of gravity, which he called the general theory of relativity. He then had to find a new name for his first theory, the one from 1905 that dealt with constant velocity but not gravity. He called it the special theory of relativity. It was an unfortunate choice of name in hindsight. It would have been much clearer for future generations if he had just called the first one relativity and the later one extended relativity or the theory of gravity, but the name stuck, and so we have special and general relativity. So where does this word relativity even come from? To understand it, just try to answer one simple question. What is your current velocity? Don't rush. Just take a moment and answer it in your mind. Did you say 0 because you were sitting or lying still? Even if you were on an airplane travelling at 35,000 feet, you might still instinctively say 0. You're buckled into your seat, told not to move around the cabin, so your velocity relative to the airplane must be 0. Or maybe you did say 550 miles per hour, the approximate cruising speed of a modern passenger jet. Or maybe you are listening to this on a slow boat at the mouth of the Amazon River, and you correctly stated your speed as 1,000 miles per hour, the rotational speed of the surface of the Earth at the equator. Or, if you know your astronomy, you might have included the Earth's velocity as it orbits the Sun and said 18 miles per second. And if you were to account for the Sun's velocity as it orbits the centre of the Milky Way galaxy, and the Milky Way's own velocity as it hurtles through the vast emptiness of intergalactic space, your answer might have been something like 1,000,000 miles per hour. So, which of these answers is correct? The surprising truth is that they all are, every single one. Your velocity is not an absolute property. It depends entirely on the platform you use as a point of reference, what physicists call a reference frame. Your reference frame could be the ground, the airplane you are in, the Earth's core, the Sun, or the cosmic microwave background radiation that fills the entire universe. You and a person on the ground don't argue about your velocity. You both understand and agree that you are at rest relative to the plane, and moving at 550 miles per hour relative to the ground. There is no contradiction. And now for the shocking, mind-bending heart of relativity. Not just velocity, but time itself depends on the reference frame. The universal, absolute time that you were taught about by your parents, the idea of a single cosmic clock ticking away for everyone, everywhere, simply does not exist. In different reference frames, you don't just measure different times on the clock, you experience a different rate of the flow of time itself. That means the interval between two events, between two ticks of your watch, is not universal. It is relative. Many popular books and documentaries on relativity say that observers moving at different speeds disagree with each other about measurements of time and space. This is, to put it bluntly, nonsense. Even the greatest physicists sometimes use these words as a kind of shorthand, but they know they're not strictly true. Observers in relativity disagree, only to the same extent that they disagree about the speed of a person on an airplane. They all know that velocity is relative and depends on the chosen reference frame. And if they have studied Einstein's work, they know the same is true for time. The real glory of relativity is not that everyone disagrees, but that everyone, everywhere, always agrees on the results once they correctly apply the mathematical transformations between their different reference frames. The theory provides a universal framework for agreement. Einstein showed that the faster a reference frame moves, that is, the closer its speed gets to the ultimate cosmic speed limit, the speed of light, the slower time flows within that frame when compared to a stationary frame. Let's take a concrete example. Imagine you're in a spaceship moving at 97% of the speed of light relative to Earth. 1 year passes for you between your birthday celebrations on the ship. You age by 1 year. But in the Earth's reference frame between those same 2 birthdays of yours, not 1 year passes but a full 4 years. Time on your ship, as measured by Earth, is flowing 4 times slower. An observer on Earth would say, the time interval between the 2 birthday parties for the astronaut was 4 years in our Earth reference frame, and 1 year in the spaceship's reference frame. And you, the astronaut on the ship, would say exactly the same thing, just from your perspective. You don't argue. You both know the rules of relativity. You both agree on the facts. This effect is called time dilation. There is a precise mathematical formula for it, and it is linked to a factor that physicists call gamma. The gamma factor tells you exactly how much time stretches for a moving object. At 97% of the speed of light, the gamma factor is about 4. If you spend a year on the ship, you will age by a year. But when you return to Earth, you will find that 4 years have passed for everyone you left behind. The irony is that while we struggle to even define what the flow of time truly is in a philosophical sense, we have an exquisitely precise mathematical formula for its relative speed. The relativity of time is not an abstract mathematical curiosity. It is a real, measurable fact of the physical world. When I was a graduate student in physics at Berkeley, time dilation was an everyday experience for me. I worked in a lab with elementary particles, specifically particles called pions and muons. These particles were radioactive, which means they decay spontaneously into other particles after a certain amount of time. The pions at rest in my lab had a tiny fleeting half-life, about 26 nanoseconds, which is 26 billionths of a second. But I was observing pions that were moving at a monstrous speed, a velocity of 0.999988 of the speed of light, incredibly close to the ultimate limit. And because of this speed, the half-life I measured for them was 637 times longer than the half-life for the stationary pions. Their internal clocks were ticking 637 times slower, and this measured number perfectly matched the calculated gamma factor for that specific velocity. For me, as a young grad student, relativity had been just an abstract theory from lectures and textbooks. To witness it happening in real life, to see time itself stretching in my own experiment, was a mind-blowing and unforgettable experience. Does this mean that when I fly on a commercial airplane, I actually live longer than someone who stays on the ground? Yes, absolutely. This very effect was measured with incredible precision back in 1971 by 2 physicists named Joseph Hafeel and Richard Keating. They used a regular commercial jet and a set of ultra-precise atomic clocks. Their entire budget for this historic experiment was only $8,000, most of which was spent on round-the-world airline tickets for themselves and a separate seat for their precious clock. The groundbreaking results were published in one of the world's most prestigious scientific journals, the journal Science. At a typical cruising speed of 550 miles per hour, every day of your life is lengthened by approximately 29 nanoseconds. It's not much, but to put it in perspective, my modern iPhone can perform about 41 computational operations in that tiny sliver of time. Hafeel and Keating were able to measure this minuscule time dilation and confirm Einstein's predictions to a high degree of accuracy. The effect is even more pronounced and practically important for the satellites of the Global Positioning System, or GPS, which orbit the Earth at nearly 9,000 miles per hour. Calculations show that time on these satellites runs slower than time on Earth's surface by about 7,200 nanoseconds every single day due to their speed. The GPS system has to constantly and meticulously account for this relativistic effect. Radio waves, which the system uses to communicate, travel about 1 foot in a single nanosecond. If these 7,200 nanoseconds of time dilation were ignored, the system would accumulate a positioning error of almost 1.4 miles every day. Within a week, it would be useless. If you have a cell phone in your pocket, you are carrying a device that relies on and validates Einstein's theory of relativity every single day just to tell you where you are. When you move fast, your time flows slower. Your watch runs slower, but so does your heartbeat, the aging of your cells, the chemical reactions in your brain, the very movement of your thoughts, you won't notice a thing, because your entire reality is slowed down together. That is the miracle of relativity. It's not just that clocks slow down, it's that the very pace of time itself changes. This phenomenon of time dilation opens a direct, scientifically valid path to travelling into the future. If you move at a high enough speed for a long enough time, your personal time will slow down dramatically compared to the rest of the world. In what feels like 1 minute of your personal time, hundreds or even thousands of years could pass in the future of the Earth. You don't need to cryogenically freeze your body and hope that some future science finds a safe way to unfreeze it. You just need to accelerate to a significant fraction of the speed of light. Of course, there are some rather large practical details to consider. You need to make sure you don't hit even a tiny speck of dust at that high speed. The impact would be catastrophic. You need to be able to navigate back to the right place in space, where Earth will be thousands of years from now. And there is one very important catch. Once you arrive in the future, you won't find a similar mechanism to take you back to the time you came from. Time travel, according to relativity, is a one-way street. But even if you have come to terms with the idea of time dilation, with the stretching and shrinking of time, there is another of Einstein's discoveries that can cause real, deep anxiety. The popular term quantum leap originally referred to discrete sudden processes in quantum physics. But according to relativity, just such an abrupt, discontinuous change happens to the time of a distant event when you simply change your reference frame by accelerating. And this time jump, this sudden reordering of reality can be huge. We're all used to thinking that if two events are simultaneous, like a New Year's party starting at your house and another party starting at your friend's house on the other side of town, they are simultaneous for everyone, regardless of how they're moving. It seems like simple, undeniable common sense. But what if your friend isn't on the other side of town but on the moon, and his party is perfectly simultaneous with yours in the reference frame of your house on Earth? Would those two parties still be simultaneous in the reference frame of that pine from my lab, the one flying at nearly the speed of light? The obvious, intuitive answer is yes. The correct answer, according to Einstein, is no. Without abandoning the deeply ingrained concept of universal simultaneity, Einstein would never have been able to solve his puzzle. He showed that if two events occur in different places, then events that are simultaneous in one reference frame, say, happening right now, would not be simultaneous in another moving reference frame. One event would happen before the other, and which one happens first? That depends entirely on the direction and speed of the reference frame. You can actually switch their temporal order. That is what it means when people say that in relativity, the order of events can be flipped. For the party on Earth and the party on the Moon, which are simultaneous in the Earth's reference frame, the time difference as measured in my fast-moving peon's reference frame would be a staggering 828 seconds. That is a 14-minute difference between two simultaneous New Year's parties, and which event happens first, the Earth party or the Moon party, depends on whether the peon is moving from the Earth toward the Moon, or from the Moon toward the Earth. This discovery of the relativity of simultaneity seems even more disturbing to our sense of reality than time dilation. Most people find it so, but it is just as real, just as experimentally verified. And it is this strange time jump that lies at the very heart of the most confusing and famous paradoxes of relativity. Einstein changed not only our understanding of time, but also how we think about space. He concluded that not just the time interval between two events, but also the length of physical objects depends on the reference frame in which they are measured. To measure the length of a moving bus, for example, you have to measure the position of its front end and its back end simultaneously. But there's the catch. We've just learned that the concept of simultaneously is itself relative. A direct and unavoidable consequence of this is that length will also be different in different reference frames. If an object has a certain length Zel when it is at rest in its own reference frame, then in a frame that is moving relative to it, it will be measured to be shorter, and again, the amount of shortening is given by that same factor of gamma. I could also observe this space contraction effect in my lab at Berkeley. When we collided one of our fast-moving pions with a stationary proton, in the pion's own reference frame, the proton was not spherical at all. It appeared to be a very thin, flattened pancake, with a thickness that was 637 times smaller than its diameter, more like a crepe than a sphere. This dramatic change in shape seriously affected how the pions scattered or bounced off the proton, and it was this altered scattering pattern that I actually observed in my data. In the Earth's reference frame, on the other hand, it was the pion that was the compressed flattened particle. So what was really shorter, the pion or the proton? The answer, of course, is both, and neither. It all depends on the reference frame from which you are observing. Even after you think you have fully accepted Einstein's revolutionary results, some of the consequences continue to surprise and challenge our intuition. When stated in certain ways, they lead to apparent contradictions that can drive students, and even some professors, to distraction. The two most famous of these are the twin paradox, which we've touched upon, and the pole in the barn paradox. Imagine a farmer who has a 40-foot long pole that he needs to store in a 20-foot long barn. He studied relativity and comes up with a clever plan to use length contraction. He figures if he runs with the pole at a high enough speed, its length will contract to just 20 feet. For this, he needs a gamma factor of 2. He plans to run toward the barn, and his friend will shut the barn door as soon as the entire pole is inside. In the reference frame of the barn, this should work perfectly. But as soon as he starts running, the farmer has a terrifying realization. In his new moving reference frame, it is the barn that is moving toward him, and therefore it is the barn that has contracted, not the pole. From his perspective, the barn is now only 10 feet long, and the pole being at rest in his own reference frame is still its full 40 feet long. There is absolutely no way to fit a 40-foot pole into a 10-foot barn, and yet, in the barn's reference frame, the pole fits easily. So what actually happened? Did the farmer get the pole inside the barn or not? How can the answer to such a simple physical question depend on the reference frame? It's either in the barn or it's not. There must be a single, objective reality. This paradox is easily resolved if you are very precise with your words and your thinking. By inside the barn, we mean that both ends of the pole are contained within the barn simultaneously. This condition is indeed achieved in the barn's reference frame. The front end of the pole reaches the back wall of the barn at the very same moment that the back end of the pole enters the front door and the door can be closed. But these two events, the front end arriving at the back wall and the back end entering the front door, are not simultaneous in the pole's reference frame. In that frame, the front end of the pole smashes into the back wall of the barn, and only sometime later does the back end of the pole finally enter the front door. As is always the case in relativity, both observers actually agree on the sequence of physical events. They both say that both ends of the pole did, at some point, get inside the barn. It's just that in one frame it happened simultaneously, and in the other, it happened at two different times. The paradox dissolves when you abandon the illusion of absolute simultaneity. Now let's return to the twins. Consider twins named John and Mary. They're both 20 years old. John stays at home on Earth, and Mary flies off in a spaceship at a very high speed to a distant planet and then returns. Mary's speed is such that her time dilation factor, gamma, is 2. According to John, who sees Mary moving, Mary's clock is running slow, so Mary must be younger when she returns. But according to Mary, it is John and the Earth who are moving, so John's clock should be running slow and John should be younger. They can't both be right. What happens when Mary actually returns and they stand side by side? They can certainly tell who is younger just by looking at each other. This seems like a genuine, unbreakable paradox. To resolve it, once again, you have to be very careful with your words, and most importantly, you have to account for the relativity of simultaneity. On the outbound journey, John and Mary are in complete agreement about the relative nature of their observations. In John's reference frame, Mary is moving and aging slower. In Mary's reference frame, John is moving and aging slower. There is perfect symmetry. Okay, but what happens when Mary stops at the distant planet, turns her ship around and comes back? At that moment of turnaround, she changes her reference frame. Who is younger then? They can't both be, and indeed, they are not. The resolution lies in that strange and powerful time jump, in the loss of absolute simultaneity. Before Mary turns around, in her outbound reference frame, John is indeed younger than she is. This means she's celebrating her, say, 25th birthday simultaneously, with John celebrating his 22nd birthday back on Earth. But after she executes her turnaround maneuver and is in her new inbound reference frame, those two events are no longer simultaneous. In her new frame of reference, she is now celebrating her 25th birthday simultaneously, with John celebrating a much, much older birthday, perhaps his 31st. The act of accelerating and changing reference frames caused a massive, instantaneous jump forward in what she considered to be the present moment on the distant Earth. On the way back in her frame, John is once again moving, so he is once again aging slower than she is. Nevertheless, the time jump that occurred during her turnaround was so huge that when they finally meet back on Earth, John is definitively older than Mary. But isn't all motion relative? Who is to say who really turned around? Can't we just as easily argue that it was John and the Earth, not Mary, who made the turnaround journey? No, we can't. In this case, there is no disagreement about who turned around. It was Mary who fired her retro rockets. It was Mary who felt the physical forces of acceleration pressing her into her seat. Both John and Mary know that it was Mary's reference frame that accelerated, and John's that did not, or at least not significantly. In the context of special relativity, it is not true that all motion is relative. What is true is that you can do all your calculations in any inertial reference frame, any frame that is moving at a constant velocity. If a frame accelerates, you must account for the dramatic time jump of distant events that this acceleration causes. The symmetry is broken by acceleration, and the paradox is resolved. These paradoxes are just mind-bending thought experiments that arise from our deep-seated, intuitive but incorrect belief in absolute time and absolute space. But there is one more, and this one touches on something even deeper. The nature of causality and the possibility of free will. It involves tachyons, hypothetical particles that are postulated to move faster than the speed of light. Relativity doesn't strictly forbid such particles from existing. It only says that particles with a non-zero rest mass, like us or a baseball, can't be accelerated to reach the speed of light, as it would require an infinite amount of energy. But what if a particle was born already moving at a superluminal speed? Photons, the particles of light, do not accelerate to the speed of light. They move at that exact speed from the very moment they are created. So why not tachyons? If you were to discover a tachyon, you would make physics history. But I decided a long time ago that I would not bother looking for one. My reason for this borders on the religious, or perhaps the philosophical. I believe that I have free will, and the existence of tachyons would seem to violate that belief in a very direct way. Imagine Mary is standing 40 feet away from John. She has a special tachyon gun that fires bullets that move at 4 times the speed of light. She aims and fires. Light travels at approximately 1 foot per nanosecond, so her tachyons are flying at 4 feet per nanosecond. In just 10 nanoseconds, the tachyon bullet enters John's heart and kills him. A tragic event. Mary is put on trial for murder. She doesn't deny the basic facts of the case, but she insists on an unusual change of venue. She says she has the right to argue her case from any valid inertial reference frame she chooses. The judge, being well versed in relativistic physics, agrees. She picks a reference frame that is moving at half the speed of light in the direction from her to John. In the Earth's reference frame, the two crucial events, the firing of the gun and John's death, are separated by a time interval of plus 10 nanoseconds. But when we apply the equations of relativity to calculate the time interval between these same two events in her chosen moving reference frame, we get a value of minus 15.5 nanoseconds. The crucial thing here is the negative sign. It means that in this moving frame, the events happened in the opposite order. The bullet entered the victim's heart before Mary fired the gun. Mary now has the perfect alibi. John was already dead when she pulled the trigger, and you cannot, she argues, be convicted of murdering a person who is already dead. This paradox of reversed causality only works for faster-than-light signals. If a bullet moves slower than light, the order of the two events, the firing and the impact, is the same in all possible reference frames. Changing your reference frame won't help your case in court if you shot someone with a real gun. So, is the tachyon murder scenario actually possible? One possible resolution to this paradox is to conclude that in a universe where tachyon guns exist, Mary does not have free will. Even though she pulled the trigger after John had already died in her chosen frame, she had no choice in the matter. All of her actions were predetermined by external forces and influences. John died because it was inevitable that Mary would, at a later time, pull the trigger. The order of events becomes irrelevant in a deterministic universe. The paradox only arises if you cling to the belief in free will, in the idea that Mary could have chosen not to fire. That is why I do not look for tachyons. I choose to believe that I have free will. And nothing in the established laws of physics denies this possibility, as long as tachyons do not exist. It is a fascinating thought that the concept of free will, often considered purely philosophical, becomes in this way scientifically falsifiable. It makes at least one testable prediction: tachyons will never be discovered. By the way, in the story of the tachyon murder trial, Mary was ultimately convicted. When the judge declared her guilty, he explained his reasoning. He had no choice in the matter, he said. He had no free will, and therefore he could only do what the complex forces of the universe acting upon him made him do. The heart of each of these paradoxes lies in the deeply non-intuitive nature of simultaneity. It is much easier for our minds to accept that time can slow down, or that moving objects can get shorter than it is to get comfortable with the radical concept that when we say the word now, that word has no universal, objective meaning. But there is another paradox, or rather, a surprising feature of our universe. It is a way to bring distant objects very close together in a very short amount of time. If you take the distance to a faraway galaxy and divide it by the time that has passed in our experience since the light from it was emitted, the resulting velocity, the rate at which the distance between us and that galaxy is increasing, can be much, much greater than the speed of light. Yet this behavior does not violate the theory of relativity. The universe is expanding. This was the great discovery of Edwin Hubble in the 1920s. But what exactly is expanding? It is not that matter is flying apart through a fixed static space, like shrapnel from an explosion. It is that space itself is expanding, stretching, growing. This incredible idea, based on Einstein's general theory of relativity, was proposed by the Belgian priest and physicist Georges Lemaitre, even before Hubble's final observational discovery. The galaxies, for the most part, are essentially at rest in their local cosmic coordinates. The apparent recession of galaxies, Hubble's law, arises not from the movement of the galaxies themselves, but from the continuous expansion of the space between them. This is another example of Einstein's discovery of the rubbery, dynamic nature of spacetime. This means that the rate of change of distance between two very distant galaxies is not limited by the speed of light. It can be anything. This does not violate relativity because nothing material is actually moving faster than light through its local space. It is just that more space is being created between the objects. This concept is at the very core of the modern cosmological theory of inflation, a theory put forward by the physicists Alan Guth and Andre Linde in the early 1980s. They were trying to solve a deep puzzle about the universe, its remarkable, almost unbelievable uniformity on very large scales. If we look 14 billion light-years in one direction into space, and then 14 billion light-years in the exact opposite direction, we see regions of the early universe that could never have been in causal contact with each other. There are 28 billion light-years of distance between them, and the universe is only about 14 billion years old. Light has not had enough time to travel from one to the other. So how did they agree to have almost exactly the same temperature and density? The theory of inflation proposes a stunning answer. Once upon a time, they were very, very close together in intimate thermal contact. And then, in the very first fraction of a second after the Big Bang, the universe underwent a period of super-fast exponential expansion. Space itself inflated at an unimaginable rate, carrying these now distant regions far away from each other in the blink of an eye. This was not movement through space, but the creation of new space between them. This superluminal phenomenon, this stretching of space-time itself, brings us to the very heart of the matter. Because if space is expanding, if new space is being created every moment, what is happening to time? The greatest breakthroughs in our modern understanding of time belong to Einstein, but even he completely failed to explain its most fundamental and obvious feature, the fact that it moves. Time, in his theories, is often treated as a fourth dimension, similar to the three dimensions of space, but it's fundamentally different in our experience. It progresses. The past is very different from the future. The past is fixed and unchangeable, while the future is open and undetermined. And that special fleeting moment we call now seems to travel relentlessly forward through time. Why? Into this profound mystery stepped the British physicist Sir Arthur Eddington. He was a brilliant physicist, an accomplished astronomer, a deep philosopher, and a wonderful popularizer of science. In 1919, it was he who led the famous eclipse expedition that measured the deflection of starlight near the Sun, providing the first dramatic experimental confirmation of Einstein's general relativity and making Einstein a global celebrity overnight. Eddington thought deeply about the nature of time. The great thing about time is that it goes on, he wrote with characteristic simplicity in 1928. But this is an aspect of it which the physicist sometimes seems inclined to neglect. Eddington did not explain why time flows, but he offered the most famous and enduring explanation for its direction. He asked a question that seems almost childishly simple. Why does time go forward and not backward? This question seems stupid until you think about it deeply. As we've discussed, the fundamental laws of physics, at the microscopic level, do not seem to distinguish between the past and the future. They are time-symmetric. But Eddington not only asked this silly-sounding question, but he also gave an answer that still intrigues and dominates the thinking of physicists to this day. He argued that there is only one fundamental law of physics that has an arrow of time built into it: the second law of thermodynamics. This law states that the entropy, which is a measure of the disorder or randomness or chaos in a system, in an isolated system, always either stays constant or increases. It never, ever spontaneously decreases. Imagine a film of a cup falling off a table and shattering into 1,000 pieces on the floor. You can easily tell which way the film should be played. Cups do not spontaneously assemble themselves from scattered shards and then jump back up onto a table. That would be an event of such extreme improbability as to be considered impossible. Heat naturally flows from a hot object to a cold one, not the other way around. Car crashes destroy objects. They do not spontaneously assemble them from scrap metal. These are all everyday manifestations of the second law of thermodynamics. Entropy and time seem to increase together. They are correlated. But Eddington went a crucial step further. He suggested that the increase of entropy is the cause of the arrow of time. Time moves forward, he argued, because the total amount of disorder in the universe is relentlessly growing. But why should disorder grow at all? The answer, according to modern cosmology, lies in the fact that our current universe, for some unknown reason, started out in an extraordinarily ordered state. It has very low entropy. We have enormous, highly concentrated collections of matter in the form of stars and galaxies, separated by vast, nearly empty voids. This high degree of orderliness is extremely improbable from a statistical point of view. And because the universe started in such an ordered state, it has only one way to go: toward greater disorganization, toward thermal equilibrium, toward a state of maximum chaos. Time moves forward because our universe is surprisingly and mysteriously well organized. Hubble's discovery of the expanding universe provided a physical explanation for this continued state of low entropy. The universe is ordered because it is relatively young. In the early, hot, dense, compressed state of the universe right after the Big Bang, matter was in a state of relatively low entropy. The subsequent expansion of space created a huge amount of room for new states to be occupied, for entropy to grow into. The universe is only about 14 billion years old, and it simply has not had enough time to reach its final state of maximum chaos and high entropy, the so-called heat death of the universe. This explanation sounds very convincing and elegant. It links our most intimate everyday experience of the unidirectional flow of time to the most large-scale cosmological processes in the universe. But I have to confess something. I believe this standard entropy explanation for the arrow of time is deeply flawed and almost certainly wrong. I think it is another one of those incorrectly placed puzzle pieces that is preventing us from seeing the whole, true picture. Civilization, and indeed life itself, is built on the local decrease of entropy, not its increase. We build ordered houses from disordered piles of bricks and wood. We write ordered books from a random alphabet of letters. We create complex, functional cities. Trees take scattered, simple molecules like carbon dioxide from the air and use sunlight to build complex, highly ordered structures like leaves and wood. The entire history of life and humanity is a history of fighting against chaos, of creating pockets of order, not of succumbing to disorder. Of course, the total entropy of the universe does increase in this process, primarily through the waste heat we dump into our environment and ultimately into space. But our immediate subjective experience, our personal arrow of time, is defined by the creation of local order. Besides, where is the main reservoir of entropy in the universe? It's not in the stars and planets and galaxies. It is calculated that 10 million times more entropy is contained in the cosmic microwave background radiation, the faint thermal afterglow left over from the Big Bang that fills all of space. And the entropy of this radiation isn't changing. It has been essentially constant for billions of years. Even more, by a factor of billions of times, the greatest amount of entropy in the universe is calculated to be hidden away inside the supermassive black holes at the centers of galaxies. But this enormous store of entropy is, for all practical purposes, at an infinite causal distance from us, locked away behind event horizons. How can something so remote and inaccessible possibly determine the direction of our arrow of time here and now? And finally, there's the discovery of the so-called God particle, the Higgs boson, in 2012. The standard model of particle physics states that in the very, very early universe, all elementary particles were massless, and in this primordial era, even as the universe expanded, the entropy of this massless matter did not grow. It remained constant. If the flow of time were driven by the growth of entropy, then time itself would have stopped in that very first moment of creation. We would have never left that initial era. But time did not stop. The universe continued to evolve. If we tentatively pull out this misplaced puzzle piece, the idea that entropy causes time's arrow, the picture might start to come together in a new and more coherent way. Let's go back to the very essence of the beginning, to the Big Bang. In the modern cosmological model, it is space itself that expands. But what if the Big Bang is not just an explosion of three-dimensional space, but an ongoing creation of four-dimensional spacetime? Then, along with new space, new time is constantly being created moment by moment. This is the flow of time, the continuous ongoing addition of new moments to reality. The future does not exist yet, despite how it is often drawn on static space-time diagrams in physics textbooks. It is being actively created, right now. And the moment we call now is this very boundary, the shock front, the leading creative edge of time emerging from nothingness. This idea helps to explain why we feel ourselves to be so firmly rooted in the present. The past already exists. It is determined, recorded in the fabric of space-time. What has been, as the ancient poet wrote. We cannot change it. And now is the only moment when we can exert influence, the only moment when we can apply our free will to shape what is to come. The existence of free will could have been plausibly denied in the old days of deterministic classical physics in Newton's clockwork universe. But the advent of quantum mechanics in the 20th century showed that the world, at its most fundamental level, is fundamentally unpredictable. If you have two absolutely identical radioactive particles, one will decay at one time and the other will decay at a different time, and there is no way, even in principle, to predict which will decay when. Their future is not predetermined by their past. This fundamental uncertainty, this inherent fuzziness of physical reality, leaves room for something else to enter the picture, for a non-physical reality, for choice. It is our free will that allows us to direct the local flows of entropy. We cannot stop the overall growth of entropy in the universe, but we can choose how and where it will happen. We can direct the process so that locally, in our immediate surroundings, entropy decreases. We can choose to build, not to destroy. We can choose to create order from chaos. And this is the deepest meaning of the moment now. It is not just a point on a pre-existing timeline that our consciousness is passing through. It is the only instant when reality is malleable. It is the moment when the almost unthinkable is possible, the creation of new order. It is the moment when we cease to be merely a consequence of the past and become the cause of the future. Of course, profound mysteries remain, and perhaps the greatest of them all hides in the strange story of a cat that is simultaneously dead and alive. This famous thought experiment, conceived by the physicist Erwin Schrödinger as a way to mock what he saw as the absurdities of the new physics, turned out to be deeply prophetic. Quantum mechanics, with its probabilistic nature, its spooky action at a distance, and its mysterious collapse of reality at the moment of observation, is the final and perhaps most challenging frontier in our quest to understand the nature of time. Schrödinger imagined placing a cat in a sealed box, along with a single radioactive atom. There is a 50% chance that the atom will decay in 1 hour. If it decays, it triggers a mechanism that releases a poison, and the cat is dead. If it does not decay, the cat remains alive. But according to the strange rules of quantum mechanics, until we open the box and make a measurement, the entire system exists in a state of superposition. The mathematical wave function that describes reality contains 2 equal parts, one part corresponding to a dead cat and the other part corresponding to a live one. In a very real sense, the cat is simultaneously dead and alive. Schrödinger and his friend Albert Einstein considered this conclusion to be utterly absurd, a clear proof of the failure and incompleteness of the quantum theory. But their younger colleagues, physicists like Max Born and Werner Heisenberg, did not back down. Yes, they admitted, it sounds ridiculous, but so did time dilation and length contraction when they were first proposed. Nearly 100 years have passed since that debate, and today, the vast majority of physicists accept this strange picture of reality, the so-called Copenhagen interpretation of quantum mechanics. The inherent absurdity of the situation has never been truly resolved. We have mostly just learned to ignore it and shut up and calculate, as the saying goes. But what if it is precisely in this act of measurement, in this strange and unexplained collapse of the wave function, from a state of many possibilities to a single actuality, that the true mechanism of the flow of time is hidden? When we look into the box, we only seem to affect the future amplitude of the wave function. The future becomes definite. The cat is either alive or it is dead. But we do not affect the past amplitude, the part of the wave function that described the cat as being in a superposition of both states. Here, in the act of observation, an asymmetry arises that distinguishes the past from the future. The problem is, we still do not have a complete physical theory of measurement. We do not know what exactly it is that causes the wave function to collapse. Does it require a conscious human observer? Is the cat itself an observer? What if a person is in the box instead of a cat? Modern physics has no definitive answers to these deeply troubling questions, but there are experimental facts that make the situation even stranger and more wonderful. An experiment conducted by Stuart Friedman and John Clauser at Berkeley in 1972 proved that Einstein was wrong in his most fundamental objections to quantum mechanics. They used a bizarre phenomenon that Einstein had famously derided as spooky action at a distance, and which we now call quantum entanglement. Imagine you create 2 particles, 2 entangled photons for instance, that fly off in opposite directions at the speed of light. Their properties, for example, their polarization, are inextricably interconnected. If you measure the polarization of one particle and find it to be, say, vertical, you instantly know that the polarization of the other particle is horizontal, even if that other particle is now on the other side of the galaxy. The act of measuring one particle instantly collapses the wave function of the other, distant particle, and this happens instantly, faster than light. Einstein thought this was impossible, a clear violation of his principle of causality. He believed that the particles must have some hidden, predetermined properties that they carried with them from the moment of their creation, and that quantum mechanics was simply an incomplete theory because it could not describe these hidden variables. The Friedman-Clauser experiment and many subsequent more sophisticated ones, including a recent landmark experiment at Delft University, have proved beyond any reasonable doubt. Spooky action at a distance is real. There are no hidden variables. Reality really does seem to collapse in this non-local, faster-than-light way. This does not mean we can send information faster than light. A rigorous no-communication theorem has been proven, so causality in the sense of sending signals is safe. But it does mean that at the very foundation of our physical reality lies a deep and mysterious non-locality, a kind of holistic connection between distant parts of the universe that seems to ignore space and perhaps time itself in our usual, everyday understanding of those terms. And here we return to the beginning of our journey, to the fundamental laws, to Hilbert's dream that everything in physics must be derivable from a clear set of axioms. Perhaps the axiom that we have missed all this time concerns not just the geometry of space and time, but the nature of information and the fundamental role of the very act of knowing. It is in this tangled and beautiful web where the grand cosmology of the Big Bang continuously creating new time and the strange intimacy of quantum mechanics collapsing reality at the moment of now intertwine, that the ultimate solution to the mystery of time may lie. Time flows because the universe itself gives birth to it, moment by moment. And the now that we inhabit is the very instant when, from the infinite shimmering ocean of quantum probabilities, under the influence of a mysterious mechanism of measurement that we do not yet understand, a single, concrete, our own, reality crystallizes into being. It is the moment when we are not just carried along by the relentless current of time, but become the very observer who, by opening the box, decides the fate not only of the cat but of the entire universe, and in that quiet act of becoming, the river of time flows on.